thank the organizers for the invitation and for the opportunity to speak. And thanks to all of you for coming for the fifth talk in the day. So yeah, so I'm going to talk about joint work with Swarnava. So he mentioned some of the things in his talk yesterday about conformal blocks. So we'll see more about this. So yeah, so in this title, I'm talking about crossed modular categories and the Berlin formula for twisted conformal blocks. So if you remove crossed and twisted, that would be the classical story about modular categories and the Berlin formula for conformal blocks. So I'm going to talk about the twisted setting. So basically, we have a simple Lie algebra over C, and now this twisting, this twisting comes from a finite group acting on this Lie algebra. Now take any element of the finite group, small gamma. So it determines a finite order automorphism of the Lie algebra. And yeah, so by this, I denote the order of this element in the group, and I take the corresponding root of unity. And now we consider the Lorentz series in C, and we have an action of this element on this Lorentz series ring by scaling the T by this, the inverse of this particular root of unity. So yeah, so we have seen maybe in Dennis's talk a version of some of these things. So in this setting, we can define a twisted affine Lie algebra. So so we form this loop algebra. Now there is gamma acting on the G and gamma acting on here according to this. So we take the gamma action here and take the gamma invariance. So that's the loop, that's the twisted loop algebra. And then we take a central extension of this. So, so basically this small c is a central element. And the Lie bracket is given by this formula. So if there was no central extension, we have seen this, the first part in a couple of talks today. But I'm taking this central extension. So basically you will get this factor. So here, this is the normalized killing form on the finite dimensional Lie algebra. And then I divide it by the order of this element, and then multiplied by the residue around t equal to 0 of G times df. So, so this is the twisted affine Lie algebra. And now we fix a positive integer called the level. And so we have a certain category of integrable level L representations of this twisted affine Cas-Moody algebra. So the level means that the central part of the Lie algebra, it acts by scaling by L. So that's the level. So what do we know about this? So this category is a finite and semi-simple abelian category with finitely many simple objects. So once you fix a level, there are only finitely many simple integrable representations of this twisted affine Lie algebra. And they are parameterized by a certain finite subset of the dominant integral weights for this fixed point. So this is a finite dimensional reductive Lie algebra. And so the simple objects of this category are parameterized by a certain finite subset of this. And how do we construct these? So first, if we take a lambda in this finite set, so that corresponds to a finite dimensional representation of the fixed point Lie algebra. And now inside the, inside this twisted affine Cas-Moody algebra, we have, the power series, G tensor the power series. So these are the positive loops or the non-negative loops. And from this, there is an evaluation map to the fixed point Lie algebra. So we get a representation of, this non-negative part. So this is like a parabolic subalgebra. So yeah, so this part acts on this by the, this is a finite dimensional representation of this to begin with. and the central part acts by L. So we define an action of this, and then we can take the parabolic Verma module, which we induce from this sub algebra to the whole algebra, and this has a unique maximal subquotient, and this I denote by H lambda. So this is how you construct all the simple level L integrable modules for the twisted affine Kasmuri algebra. So, we have a finite group acting on our Lie algebra, and for every element of the finite group, we have a certain finite semi-simple abelian category. So, okay, so I'm just saying what structure do we immediately get from this picture, right? So now let's take two elements G, gamma in our finite group. Now, we have the twisted affine algebra for gamma, and we have the twisted affine algebra for G, gamma, G inverse. Yeah, and basically, there is so the conjugation action, basically the action of this G on this gives a natural identification between these. Basically, and this gives us an gives us a functor between these two categories. And once you take all these categories together, we sort of get a graded category, and we get an action of gamma on this graded abelian category, right? Another structure that we have is if we take an integrable representation of level L, there is a notion of restricted dual, and the restricted dual is naturally a representation for the twisted affine algebra, not for gamma, but for gamma inverse. And moreover, if you take the double dual, it's canonically identified with H, right? So there is a duality operation which takes this abelian category to the abelian category corresponding to gamma inverse, and this is a contravariant involution. And the double duality is the identity. And moreover, this is compatible with the gamma action, right? So this gives a gamma action, and this is compatible with the gamma action. And another important object here is this vacuum object at level L. Basically, you take now, this is the untwisted. So 1 here denotes the identity element of our finite group. So that's the usual untwisted affine algebra, and you have so basically induced from the trivial representation. So that's called the vacuum representation at level L. So this vacuum representation is self-dual, and it is gamma invariant. So basically all these structures, so we call them, this is the notion of a gamma crossed abelian category. So basically it's all these structures, and I call such thing as a gamma crossed abelian category. So next I want to talk about the gamma crossed modular category. So a gamma crossed modular category is a certain additional structure on a gamma crossed abelian category. And this, so first of all, you should have a gamma crossed abelian category, which means C has a grading by gamma. And moreover, there should be a monoidal structure. So there is see, we have a gamma crossed abelian category, which means there is a distinguished object, which I'm calling 1 here. And okay, so so the additional structure is this monoidal, the structure of a monoidal category. And so this structure should satisfy these conditions. For example, the grading should be compatible with this tensor product or the monoidal structure. Secondly, we have a gamma action on C, that's part of but now we demand that this should be a monoidal action. And remember, we also have this duality functor. So we want that this monoidal category should be rigid. So this notion of rigidity came in the previous talk as well, which means there is and every object has a left and right dual. But here we also demand that this rigid duality agrees with the original duality that we began with. right? So and we have this identification of the double duality with the identity functor. That's part of the structure of a gamma crossed abelian category. But here we demand that this identification should be monoidal. And the monoidal identification of the double duality functor with the identity functor, and it should satisfy a certain, realness condition. So that is known as a ribbon structure. So we should have this, and this crossed braiding. So the next important part of the structure is crossed braiding. So in a braided monoidal category, you would demand that X tensor Y should be isomorphic to Y tensor X. But now, so there is a twist here. So basically, if you take X to be an object in the gamma grade, right, and Y is any object, so then X tensor Y, there should be natural isomorphism between X tensor Y and gamma of Y tensor X. So remember, X, this object X is the one which lies in the gamma component. And then once you want to swap with it, you need to put you need to act by this gamma on the Y. And then you can swap X and Y.
What is the grade of the?
No, our category is graded. So it's a C gamma crossed abelian category. So yeah, so let me just go back here. So
but that isomorphism won't preserve grade because you change the grade of.
So the isomorphism, yeah, yes. The grade, yeah. Okay, yeah, the action, yeah, I forgot. Yeah, so yeah, actually, if you see the grade, the action takes one grade component to another grade component. And if you see here, if this lies in gamma and this lies in delta, this again it will lie in the same thing. So I mean, this lies in what gamma delta gamma inverse, and then again, so it's basically it's conjugation. So this lies in the conjugate grade, yeah, and and this data should satisfy certain compatibilities like the hexagon axiom and the unit axiom. And moreover, so I'm saying gamma crossed modular. So this word modular, it's so there is a notion of a modular fusion category. So the the trivial graded component should be a modular fusion category. So basically, this modular fusion category. So this condition, the last condition, is about the non-degeneracy of a certain matrix known as a S matrix. So I'll come to the S matrices later in the talk, but this is the condition which is it can be formulated in many equivalent ways, but one of the ways is that a certain matrix known as S matrix should be invertible. So so that is the notion of a gamma crossed modular fusion category. And now so we saw that this category, which is basically obtained from if you have a group, if you have a finite group and acting on a simple Lie algebra, then we had a gamma crossed abelian category. So now our main result is that this is not just a gamma crossed abelian category, but it naturally has the structure of a gamma crossed modular fusion category. And the rest of the talk will be about how to get this additional structure. Okay, so here in the beginning, I've put this restriction that this gamma action on G should preserve a Borel subalgebra. So yeah, so this is part of our work which came a few years earlier, but we are working on our current project, which so to remove this assumption. So basically, you can forget this assumption, but that's part of ongoing work. So. Okay, so so that's the goal to how to define. So we have a gamma crossed abelian category, and how can we upgrade it to a gamma crossed modular fusion category? So what do we need to do? We need to define tensor products. So one thing that we have to do is we have to define the tensor product. So given a bunch of objects, right, AI in C gamma I, we need to define their tensor product, which will be an object in C gamma 1, gamma 2 in their product. Okay, but this is the same as defining home from an arbitrary object to this object. So defining this object is the same as defining these home spaces, But now we also want our category to have a duality. If the category did have duality, then this Hom space would be identified with this space. Where now remember, for an object in this, the dual A is an object here, but the dual lies in, you have to take the inverse of that, right? So basically this lies in gamma 1 grade, this lies in gamma n grade, and this lies in gamma n inverse, so on. So basically if you multiply all these grades, you get 1, right? So what we basically need to do is that given a bunch of objects in these graded components, and so with the grade, the grades satisfying this relation, we must assign a finite dimensional vector space that will play the role of this. And basically this will define the relevant tensor product. But of course, our tensor product has to satisfy associativity and various things. So that will put some compatibility conditions between these vector spaces. So that's the idea. So how do we define these vector spaces? So that's going to be defined using twisted conformal blocks. So okay, so yeah, and it is going to be defined using twisted conformal blocks using something known as a C extended gamma crossed modular functor. So I'll explain what is a modular functor. But essentially, from these modular functor, you can define these spaces. Okay, so yeah, so the way we proved this is we showed that twisted conformal blocks define a C extended gamma cross modular functor, and then we proved this theorem, which says that once you have such a modular functor, you get a gamma crossed modular fusion category. So yeah, so just going over some history. So basically, if there was no group acting on G, this is the classical work which originated in the work of physicists, which is known as the WZW model, and there's the classical Verlinde formula in this setting. And the mathematical foundations were worked by many people, so in particular Tsuchiya Ueno Yamada and so many other people. So it originated in the work of physicists, and then it was made mathematically rigorous by various people. And then the twisted story, there are many people have worked in this. So our work builds on some of these works. In particular, we will use the work of Hong Kumar, and I'll say where we use it. So in the classical story, what you get is that if you have an untwisted affine Lie algebra, then the level L representations has a natural structure of a modular fusion category. And this structure comes from conformal blocks. And the conformal blocks define a modular functor. So now basically we generalize this to the crossed situation where you have a finite group acting on your Lie algebra. Okay, so in this story, so now I want to sort of say what is a modular functor and what are conformal blocks. But these are gamma crossed modular functors. So we suppose we have a possibly ramified gamma cover of a curve. So here C is a smooth projective curve of genus G, and it has n mark points. And we have also chosen lifts of these mark points here. And this curve can have nodes, that's allowed. But what we want is that outside these mark points, once you remove the mark points and once you remove all the nodes, the covering should be unramified. So that's so that is known as an admissible gamma cover. So it's an admissible gamma cover is something which is basically this data which satisfies these conditions. One thing to note is that in particular we have this group gamma is acting on the top curve, and such that the stabilizer of any point is a cyclic subgroup. So even for the node, I mean, we impose this. So for the smooth point, it is clear, but for the nodes also, we impose that the stabilizer is a cyclic group, and the stabilizer should not interchange the branches of the nodes. So that's part of the condition of being an admissible cover. So for any point in the top curve, its stabilizer is a cyclic group. Moreover, this cyclic group comes with a preferred generator, because we have this preferred root of unity, and because of this, in our curve we have mark points below, but we also have chosen lifts above, and so here is the stabilizer of this point in the top curve, and we get a generator of this stabilizer. Basically, it's determined by this particular root of unity. So basically, once you have such an admissible cover associated with each point above, which is each mark point above, we have an element of our finite group, and we get a so we had gamma 1, gamma 2 up to gamma n associated with such a cover. Another thing that we need to do, so basically this is sort of the global picture, but to compare things with the local, basically to relate this to twisted affine Cauchy-Moody algebras, we will need to choose parameters, local parameters at the points here, such that the corresponding power is a formal parameter below. So these are called special formal parameters on the top curve. So basically, this gives us an identification of sort of this completion of the top curve at this point, and the this Laurent series ring. And see, there is this gamma I action on this, because gamma I is the stabilizer, and there is a gamma I action here which we defined in the first slide. Okay, maybe this action is up to, yeah, so basically, yeah, maybe up to an inverse, but yeah. Okay, and moreover, we can now take the moduli space of all such admissible curves. So this is the, so we have the moduli stack of, so the data is, we have some admissible covering, which has these mark points and these special formal parameters at the top curve. So actually, what really matters is just the derivative at 0 of this special parameter. But yeah, we can take, yeah. So I mean, there are two versions of this stack. But yeah, so anyway, we do have such a stack, and so so this has a very we are allowing nodal curves here. So basically, the nodal curves will define some boundary divisor in this stack, and the open part will be the ones where these are smooth curves. Okay, so now remember that we have okay. So suppose now you have some gamma 1 up to gamma n. We have n elements of the group, and then we have these twisted affine Lie algebras. We take their direct sum, and we go modulo this central subalgebra, which this has, everything has a central component. So this direct sum has a central component of dimension n, but we go modulo this subspace, this n minus 1 dimensional subspace, where the sum is 0. And now what happens is, since we are taking all the representations have a level L, it means that this Lie algebra, if you take this tensor product, this direct sum acts on this tensor product, and this acts trivially because they are all of the same level. So it acts trivially. So we get an action of this quotient on this tensor product. And now, if you have an admissible cover, right? So we have these parameters, right? So now if you expand these, okay, so what do I have here? So I have, so basically look at, so I'm taking the curve, I'm removing the orbit of all the marked points above. right? And so then I'm taking maps from this punctured curve to G, which are gamma equivariant. Okay, so this is this is a Lie algebra. It's basically all maps from this punctured curve to G, which are gamma equivariant. And now what you can do is you can, you have around each puncture, you can take a punctured formal disk and so basically expand along the formal parameters at every marked point here. That will give you a map here. And it will give you, basically this is a Lie algebra map because of the residue theorem. That will make this, in fact, a Lie algebra map. So remember, if we take this tensor product, right? So if we have a bunch of representations of these twisted, if you have a bunch of integrable representations of these twisted affine algebras, and we take, they're all level L, then this tensor product has an action of this Lie algebra and hence an action of this Lie algebra. So now I can define this space of conformal blocks. Basically, it's you take this tensor product and take the co-invariants with respect to this Lie algebra. So this is the vector space of twisted conformal blocks. And now what you can do is we can work in families of such admissible covers, and this gives us a sheaf of conformal blocks on this moduli stack. Okay, so here I've put gamma bar, which means these are admissible covers which have the specified, so I'm calling this the monodromy data. So these are the admissible covers which have a specified monodromy data. Okay. Yeah, so here basically, we have lots of admissible covers. Lots of such stacks, we can vary G, N, and these monodromy data. So, right. So basically what we show, yeah, so here again, I've put this first assumption of gamma preserving a Borel in bracket because, so that's the, in our old work, but we are working to remove this assumption. So yeah, so you have these various moduli stacks of gamma, of admissible gamma covers. And on these stacks, you have different, if you take different objects, if you take different integrable representations here, you get different sheaf here, right? So you have lots of these sheaves, you have lots of these moduli stacks, basically, and all these satisfy certain compatibility conditions. And basically, these compatibility conditions are what we call the axioms of the gamma crossed modular functor. So a gamma crossed modular functor is basically, you should have various collection of sheaves on various moduli stacks, and they should satisfy these compatibility relations. So, so what sort of compatibility relations? So, in fact, these sheaves are in fact vector bundles of finite rank, and they furthermore admit projective, they have a flat projective connection. So log connection, yeah, so I said that this moduli stacks, they have boundaries. So on the open part, they have a they have a flat projective connection, and at the boundary, there is with logarithmic singularities at the boundary divisor. Okay, so that's one of the things. So there should be this connection, and there should be these should be vector bundles. And these moduli stacks, they have various sort of if you have if you're not looking at covers, if you sort of so for example, you have a map, let's say from M03 cross M03 to M04 by, so choose a point here, and glue them. You will land in the boundary of this. So the factorization axiom has to do with the, so basically you have some vector bundle here. Its pullback should have a specific form. That's the factorization axiom here. And somehow, this also has to be compatible with this projective connection. And what is propagation of vacua? So you can, if you have n+1 mark points, you can forget 1 mark point. And suppose this extra marked point has the vacuum object attached to it. That should not change the conformal blocks. That is the propagation of vacua. That is the propagation of vacua axiom. That would be the connection. Yes. Yes, in genus 0, yes, that would be the analog of the Nishnik. In the untwisted, yes. Yeah, by the way, this, this factorization and particularly applied to this picture gives the associativity of the tensor product. So again, even in the twisted setting, this factorization will give the associativity. This projective connection, it sort of gives this braiding. You're allowed to move the marked points across each other, and so that gives the braiding. Okay, so so here basically, parts of these results were proved by Jiuzhu, Hong, and Kumar. For example, this factorization and the connection on the open part, and but factorization. And this propagation of vacua. But so I think this. About this factorization, we need to also not just the pullback of these sheaves, but we also need to look at the connection. You need to take the specialization of the connection, and then there is some compatibility with the specialization that needs to be checked. So, and there are various functorialities, and there are some other conditions. So basically, if you we defined, so we have this twisted conformal blocks, this bunch of vector bundles on these moduli stacks, and they satisfy these nice axioms. And this defines a gamma cross modular functor. And so once you combine it with the result that I mentioned earlier, that a gamma cross modular functor determines a gamma cross modular fusion category, we see that this gets the structure of a gamma crossed modular fusion category. So, okay, so now, so far I have not talked about the Verlinde formula. So the Verlinde formula basically is about computing the dimensions of, so see, these twisted conformal blocks, they form vector bundles. So the question is, what are the ranks of these vector bundles? And the Verlinde formula computes the ranks of these vector bundles. So, yeah, so now let me come to that. Okay, so, but before that, so how does, I talked about these multiplicity spaces, right? So, yeah, it's, we want to define the, okay, by the way, this fusion product I'm defining by this way to avoid confusing with the tensor product. So we want to define, so we wanted to define this fusion product. And the way to do this is, suppose you have a bunch of n elements of the group whose product is 1. And suppose you have these objects hi belonging to the corresponding grade. Now you have a bunch of objects, a bunch of elements whose product is 1. So see, now you take the P1, which is the Riemann sphere punctured at n points. It's fundamental. This is the relation of its fundamental group. So basically, these elements determine a group homomorphism from the fundamental group of the punctured P1 to gamma. And this determines a gamma cover. Right? So take that gamma cover, and now take the conformal blocks corresponding to this particular gamma cover. Right? And that is how you define this multiplicity space. So that's how you go from conformal blocks. So basically this is a, the space of co-invariants. So you're taking the tensor product of these infinite dimensional representations. But when you take these co-invariants, you're left with a finite dimensional vector space. And then you basically define this fusion product to be such that this gets identified with this. Okay. So yeah, so that's how you go from twisted conformal blocks to this modular functors, and from this modular functor to this fusion product. Okay, so yeah, so basically, we want to compute the the rank of this, or the dimension of this vector space, which is the same as this multiplicity space, right? So if you let's say we wanted to somehow, if we can compute the dimension of this multiplicity space, that would give the dimension, that would give the rank of these vector bundles, right? So yeah, so here notice that over here the base curve is P1. So here we are only getting M, the genus is 0 over here. So these sort of multiplicity space, they involve only M0n, but there are some more, you can suitably modify them. And in fact, yeah, so you can do this for all vector bundles of conformal blocks. So basically every vector, every vector bundle of conformal blocks on all of these stacks, so now I'm allowing arbitrary G here, they compute the dimension of some multiplicity space in this modular fusion category. So basically this goes back to how we identify a modular functor and the structure of a modular fusion category, or a gamma cross modular fusion category. So okay, so and then so basically we prove that there is a formula for such multiplicity spaces, and even these more general multiplicity spaces which appear here. So we prove a categorical twisted Verlinde formula for this, which computes the dimensions of all these multiplicity spaces, and this will give us the dimension of all these vector bundles of twisted conformal blocks. And this categorical twisted Verlinde formula, it involves certain matrices which are known as crossed S matrices. So in the untwisted story, there are S matrices, and here we generalize this notion to crossed S matrices. So let me just define what is a crossed S matrix. So suppose you have a gamma crossed modular fusion category, and let's take an element small gamma. So one one fact is that the number of simple objects in the gamma grade equals the number of gamma stable simple objects in the identity grade. So this is a general fact about gamma crossed modular fusion categories. But as a curious corollary of this fact, we get this curious equality. So basically, this says that if you look at the number of level L integrable, irreducible representations of a gamma twisted algebra, that's the same as take the untwisted one, take the simple objects in the untwisted one, but only take those which are fixed by gamma. So this, yeah, so of course you can check this, you have the classification of all finite order automorphisms of simple Lie algebras, and you have a classification of everything here. So it's, you can check in all cases that this is true, but this sort of gives a conceptual proof of this curious fact. Okay, so yeah, so this is important that the number of simple objects here is same as the gamma stable simple objects in the neutral part. So and so what do? We take a gamma stable simple object C, and moreover we choose an isomorphism between gamma of C and C. So this choice will depend up to some scaling, and we can further reduce the choices up to roots of unity. but anyway, we choose some isomorphism, and we take M to be a simple object in the gamma grade, right? So now what we can do is we can define a scalar in this way. So C is in the neutral grade, C is in the trivial grade. So the braiding goes to M fusion C because this C is in the neutral grade. But now this M is in the gamma grade, right? So this braiding goes to gamma of C fusion M. And now we have chosen this isomorphism to C fusion M. So our C is gamma stable, right? So we go back here. So we have a map from C fusion M to C fusion M, and we take the categorical trace of this. Because our categories have a ribbon structure, it makes sense to take the categorical trace of an endomorphism. And this gives us a complex number. If you choose such a C and such an M, you get a scalar. And basically, if you collect all these scalars, you get a matrix, which we call the gamma crossed S matrix. Of course, you need to normalize this. And the matrix that you get in this way is unitary after you normalize it. So yeah, so this is the gamma crossed S matrix. So yeah, so basically it's a square matrix because of the first point here. So, and for twisted affine Lie algebras, we can compute these crossed S matrices explicitly. I mean, so what do these M's come from? These correspond to some finite dimensional representation of the fixed point Lie algebra. So it's trace of a certain, so this C will determine a certain operator, and the trace of that operator will be the entry of the crossed S matrix. So yeah, so these can be explicitly computed for this case of a finite group acting on a Lie algebra. So yeah, so basically the categorical Verlinde formula computes the multiplicity spaces in terms of these crossed S matrices. And yeah, so basically, and the multiplicity spaces are the same as the, the ranks of the bundles of conformal blocks. So yeah, so basically the dimension of these space of conformal blocks is equal to, yeah, so in this formula, see this admissible cover corresponds to some map from the fundamental group of the bottom punctured curve to gamma. And I'm taking gamma circle to be the image of this map. Right? So basically the formula has this shape. So various crossed S matrices appear here. Corresponding, see we have a bunch of simple representations in various grades. And so you have a bunch of these crossed S matrices, and this lambda is in the neutral grade, but it's fixed by this image of this, right? And yeah, so this is yeah, so the classical Verlinde formula is where basically you have no gamma acting, and it's exactly this. But in this case, what is, so in the numerator you have these various crossed S matrices, and in the denominator there is the sort of this uncrossed S matrix. Yeah, and 0 is the weight corresponding to the vacuum element.
Just a matrix.
No, this is not a.
No, the numerator. Oh, these are lambda 1.
Yeah, these are the entries of the cross state. Yeah, so these are just complex numbers. These are the entries of the matrix. Okay, so that's the twisted Verlinde formula. And yeah, so let me just do an example. Take, take D4, and you have the cyclic order 3 permutation of D4. And in this case, the fixed point Lie algebra is of type G2. And so 0 for any level, 0 is an admissible weight in the twisted affine algebra of basically D4, 3. And so, for example, take this elliptic, this cover where E is an elliptic curve ramified at 3 points with the monodromy 1, 1, 1 at all. This 1 bar, 1 bar, 1 bar are lying in this Z mod 3. So this is a particular cover ramified at 3 points, and the ramification data is this. And now if we put the same weight 0 at all the 3 points, suppose the answer depends on the level. So at level 1, this corresponding dimension is 2. And at level 2, the dimension is 3. So yeah, so basically you can compute the cross-test matrices and you compute these dimensions. So in this case, you would get a Z mod 3 crossed modular fusion category. Okay, so let me just say some remarks. So basically, this is also sort of this case. In our previous work, we had this assumption that gamma preserves a Borel. So just let me, to end my talk, the last few minutes, let me just make a few remarks. So if you take the automorphism group of the Lie algebra and it maps to its outer automorphisms, so these are the diagram automorphisms. So you have a simple Lie algebra, you have its diagram automorphisms, and G add, it's the adjoint form of the group. So that's the inner automorphisms. And this is a split exact sequence, and splitting basically corresponds to pinning of this Lie algebra. And yeah, once you fix the pinning, those are called the diagram automorphisms. Once you put these automorphisms, outer automorphisms inside the automorphisms. Okay, so given any action, so this is any action. So basically, it's a map from, it's a homomorphism from gamma to automorphisms. What you can do is you can go to the outer automorphisms, fix a pinning, and then consider the diagram automorph. So fix any pinning and consider it here, right? So this way, associated with any action, there is an associated diagram action, and these action, so both of them define the same outer action. So basically, they differ by an inner, So given any action, it is related to some diagram action, and a diagram action always preserves a Borel. Yeah. So I mean, a diagram action preserves a pinning. So in particular, it preserves a Borel. Yeah. So the diagram action preserves a Borel, and Jizu Hong and Shrawan Kumar proved that essentially the vector bundles of conformal blocks for phi and psi are closely related, and they essentially have the same ranks. So if you're only interested in computing the dimensions of the vector bundles, it's enough to consider diagram actions. So because corresponding to any action, there is a corresponding diagram action. Okay, but so here I've said essentially because, see, the twisted affine Lie algebras are different for the action and the diagram action. So you need to make some non-canonical choices. So that's why I said essentially the same, because the categories are not exactly the same. They are quite slightly different. Okay, and so let me also comment on relationship to work of Ettinghoff, Nikšić, and Ostrich. So they, so Ettinghoff, Nikšić, and Ostrich, they have given a classification. So I defined this notion of gamma crossed modular fusion category. So inside this, you have the C1, right, the corresponding to the grade 1. So you can try to classify all possible gamma crossed modular categories which have a fixed C1. And this classification is given by Ettinghoff, Nikšić, and Ostrich. And this classification is in terms of certain group cohomological data. And yeah, so So, there is some, okay, so just a minute more. So, so we have a modular, gamma cross modular fusion category corresponding to psi. So this we already have because it's it fixes a Borel. And in our upcoming work, we hope to prove that there is one corresponding to this as well. And we also plan to, how are these two gamma cross modular fusion categories related to each other in terms of this classification. So yeah, so this also we hope to do in our, yeah, so I'll stop.
Are there any questions? If not, let's thank the speaker and call it a day.